Today we're going to look at section 6.4, compound interest. So we need to understand and compute compound interest. As we saw in simple interest, an account that pays simple interest only pays based on the original principal and the term of the loan. Accounts offering compound interest pay interest at regular intervals. After each interval, the interest is added to the original principal. Later interest is calculated on the original principal plus the interest that has been added previously. After each period, the interest on the account is computed, then added to the account. Then, after the next period, when interest is computed based on the original principal and the interest that was added. So, let's look at an example here. Oksana deposits $5,000 in a CD that earns 3% compounded annually. How much is the CD worth after 4 years? So this is simple interest right here. The interest is the principal times the rate times the time. I have 5,000 times 0.03 times 4. So my interest earned 5,000 times 0.03 times 4 is $600. So the total amount would be $5,600. Now, Oksana deposits 5,000 in a CD that earned 3% compounded annually and was worth $5,627.54 after 4 years. Had Oksana invested in the CD with simple interest, how much would the CD have been worth after 4 years? Well, we calculated that as 5,600. So how much more did Oksana earn using compound interest? Well, in this case, with the compound interest, she earned $5,627.54. With the simple interest, it was $5,600. The difference is simply $27.54. So not a whole lot, but it adds up over time. That's the trick. So understanding and computing your future value. The future value of an investment, A, when the principal P is invested at an annual interest rate R in decimal form, compounded n times per year for T years, is found using the formula A equals P times 1 plus R over N to the NT power. This refers to the future value of the investment. Sometimes the formula is presented with the total number of periods N and the interest rate per period R. In that case, the formula would simply be A equals P times 1 plus R to the N. Now, in the following, compute the future value on the investment with the given conditions. So we have a principal of 7,600, annual interest rate of 4.1%, and compounded monthly for 10 years. So looking at this formula here, we have A equals P times 1 plus R divided by N over N to the NT power. So we're looking for A. We know our principal is $7,600. Bring down this 1. We know our interest rate is 0.041, 4.1% in decimal form. It's compounded monthly, so there's 12 months in a year. And then again, there's 12 months in a year, and it's for 10 years. So we're looking at 7,600 times 1 plus, and we go 0.041 divided by 12 is 0.0034, and I'm going to stop there, 2. And this would be to the 120th power. So I have 1.00342, 7600 times 1.00342 to the 120th power. Remember to do that, you use your caret button. 120, not one, there, 120. So you do 1.00342 caret 120. So let's do that. 1.00342 to the 120th power. So now I have 7,600 times 1.5063, and again, I'll go 5 decimal places. 7. So 7,600 times 1.50637. And we end up with $11,448.41. Since it's money, we rounded 2 decimal places. Okay, let's look at another example of this. Same formula. Principal is 13,250. Annual interest rate is 2.79%. Compounded quarterly, so N equals 4 for 25 years. So I'm looking at A equals the principal, $1,325, times 1 plus 0.0279 divided by 4 to the 4 times 25. So we bring down our $13,250. And we have 0.0279 divided by 4. And then I'm going to add that to 1. And I get 1.006975. And 4 times 25 is 100. So now I'm going to take this 1.006975 to the 100th power, and I end up with 13,250 times 2.00387. We'll stop there. So 13,250 times 2.00387. Then we have a final value of $26,551.28. The 25 years our money doubled. Okay, now we have Maggie invests 3,000 in an account that earns 5.1% interest compounded monthly. Monthly means N is 12. How much will it be worth in 13 years? So again, we have A equals the principal, 3,000, times 1 plus the interest rate, 0.051, 5.1% in decimal form, over the number of times compounded in a year, 12. And we have 12 times 13. Okay, so this is 3,000. And then if we do 0.051 divided by 12, and then add that to 1, gives me 1.00425. And then this is to the 156th power, 12 times 13. Then I hit my caret button to the 156, and I get 3,000 times 1.93788. So 3,000 times 1.93788. That gives me $5,813.64. So it didn't quite double. So Jacob invests $3,000 in a CD that yields 3.4% compounded daily for 5 years. How much is a CD worth after 5 years? So again, we start with A equals 3,000 times 1 plus, now this is going to get kind of wild, 0.034 over 365 daily, 365 days a year. Then we need N again, 365 times the number of years, 5. So we're going to need to use a lot of decimal places here because it's going to get really small. 0.034 divided by 365. And I have 1.00009,315. And then 365 times 5 is 1,825. So again, we go 1.00009,315 to the 1,825th power, which gives me 3,000 times 1.18529 times 1.18529, and not very much. $3,555.87. The low interest rate. So we've talked about future value. How about present value? When investing, there is often a goal to reach, such as after 20 years, I'd like the account to be worth $100,000. The question to be answered in this case is how much money must be invested now to reach the goal. As with simple interest, this is referred to as the present value. So I have a value I want in the future. How much must I put in today to get that? So the money invested in an account bearing an annual interest rate of R in decimal form, compounded n times a year for T years, is called the present value of the account or of the money. N is found simply using A. Present value equals A divided by 1 plus R over N to the NT, where A is the value of the account at the investment's end, and we always round up to the nearest penny. So let's rewrite that here so we can refer to it easily. Present value equals the amount we're looking for over 1 plus R divided by N to the NT. So if I want to have $1 million in my account, and I have 5.7% interest compounded monthly for 40 years. So my A, the amount I want, is $1 million. And I have 1 plus my interest rate, which is 0.057575 5.75 in decimal form, or 5.75% in decimal form. Compounded monthly, so N is 12. So again, I have N times T, which is 40 years. So let's do a little bit of this, and we have 1 million over and 0.0575 divided by 12. And we're going to add 1 to that to get 1.00479. And then this is 280. Now, when rounding these, when doing the calculations, you want to try to keep as many decimal places as possible within reason, especially if we start off with a bunch of zeros. So like we had 2 here, and then if you remember up here, we ended up having 4. So don't just stop at a fifth digit if the first 4 are zeros. It can make a very significant difference. So now I need to take this, and this is our 1 million divided by, and we take 1.00479 to the 280th power, which gives me 3.81141. And now I simply divide 1 million by that. 1 million divided by 3.81141. And we have 20. Oh, there's a mistake here somewhere. Oh, there's not. $262,370 and rounding up to 10 cents. So we almost quadrupled our money over 40 years. Of course, who has $262,000 laying around to make the initial investment? Okay, let's look at another one of these. The amount we want to have at the end is $175,000. Our interest rate is 3.8%. We're compounded quarterly, so N is 4 for 20 years. So my present value, what I need to deposit today to reach this goal of having the amount of $175,000 at 3.8% in decimal form, compounded quarterly, and 4 times 20. So I'm looking at 175,000 over, and then 0.038 divided by 4, and add that to 1. I get 1.0095, and this is to the 80th power. So take it to the 80th power, and I end up with 175,000 over 2.1306. 175,000 divided by 2.13062 gives me a final result of $82,135.72. Okay. Hajan turns 30 this year and begins to think about retirement. He calculates that he will need $1,200,000 to retire comfortably. He finds a fund to invest in that yields 7.23% and is compounded monthly. How much will Hajan need to invest in a fund when he turns 30 so that he can reach his goal when he retires at age 65? So first we have compounded monthly. So N equals 12. He's 30 now and he wants to retire at 65. So T is 65 minus 30, which is 35 years. A is 1,200,000. and our interest rate is 7.23%. So our present value is equal to the amount over 1 plus R over N to the NT, just as a refresher. So let's put our numbers in here. 1,200,000 over 1 plus R in decimal form, 0.073 divided by N, which is 12, all to the N times T power. So let's look at this, 0.0723, 723 divided by 12. Then we're going to add that to 1. And I have 1,200,000 over. This becomes 1.006025. And 12 times 35 is 420. And now I need to take my 1,200,000 and take my 1.006025 to the 420th power. That went up quick. 12.46478. Now simply do the division. 1,200,000 divided by 12.46478. And we get a final value of oh, I added too many zeros. Let me recalculate this. 1,200,000 divided by 12.46478. There we go. Much better. $96,271.26. Okay. So what about here? This effective annual yield. As we've seen, quarterly compounding pays interest 4 times a year or every 3 months. Monthly compounding pays 12 times a year. Daily compounding pays interest every day, and so on. Effective annual yield allows direct comparison between simple interest and compound interest by converting compound interest to its equivalent simple interest rate. We can even directly compare different compound interest situations. This gives information that can be used to identify the best investment from a yield perspective. Using a formula, we can interpret compound interest as simple interest. The effective annual yield formula stems from the compound interest formula and is based on an investment of $1 for 1 year. Effective annual yield, Y, is equal to 1 plus R over N to the N power minus 1, where Y is the effective annual yield, R is the interest rate in decimal form, and N is the number of times the interest is compounded in a year. Y is interpreted as the equivalent annual simple interest rate. So let's look at what we have here. Calculate and interpret the effective annual yield for an investment that pays a 7% interest compounded quarterly. So Y equal to 1 plus 0.07 over 4 to the 4th power minus 1. So 0.07 divided by 4, add that to 1, and I get 1.0175 to the 4th power minus 1. So take it to the fourth power, and I get 1.07186 minus 1, which gives me 0.07186 or 7.186%. This would be if we calculated as simple interest, that's what we would need to do the same as compound interest at 7%. So the compound interest gives us a little bit of a boost. Calculate and interpret the effective annual yield on a deposit earning 2.5% compounded daily. So y equals 1 plus 0.025 over 365 to the 365th power minus 1. 0.025 divided by 365. Going to add that to 1. And again, we're going to need to keep a lot of zeros here. 1.0000. And I'm going to go ahead and do 68493 to the 365th power because that is what my calculator gives me. So let's take that to the 365th power. And here I get 1.02531. And I'll stop there. Minus 1. Which gives me 0.02531, which is 2.531%. Not a whole lot of increase, but an increase still. And while 31 one-thousandths of a percent may not sound like much, when you're talking large amounts of money, it can be quite a bit. So Isabella decides to deposit $5,500 in a CD, but needs to choose between banks that offer CDs. She identifies 4 banks and finds out the terms of their CDs. Their findings are in the table below. Which bank has the best yield? So let's see. We have Smith Bank, 3.8% compounded quarterly. So what was that formula again? A equals P times 1 plus R over N to the NT. So we start out with our first bank. And what was our principal? 5,500. 5,500 times 1 plus 0.038, and quarterly means 4. And does it say how long? I guess we're talking. Oh, I'm not doing this the way that we need. We're going to use the yield formula instead on this. So yield equals 1 plus R over N to the N minus 1. That's the formula we'll use instead. Because we just want to get what the annual yield is. We don't have a time period. So at our 3.8, we have y equals 1 plus 0.038 over 4 to the fourth minus 1. We have 0.038 divided by 4. Add that to 1. I think we've done that before. I get 1.0095 to the fourth power minus 1. So I have 1.03854 minus 1. So this is 3.854% annual yield. If it were done as simple interest as opposed to compound. Looking at our second one here, this one should be a little easier. Compounded annually, so n is just 1. So I have 1 plus 0.0311 over 1 first power minus 1. 1.0311 to the first power minus 1. So it is just the same, 3.11%. Okay, so it looks like Smith's Bank's winning so far. Let's look at this 3.09% compounded daily from Town Bank. So here y, the yield equals 1 plus 0.039 divided by 365 to the 365th power minus 1. So 0.039 divided by 365. And we're going to add that to 1. I get 1.0001068 minus 1. Oops, no, that's not right. Because then I need to take that to the 365th power. 365. This gives me 1.03977 minus 1, which is 0.03977. So 3.977%. Well, now it's Town Banks in the lead. Okay, now we have a monthly. Our yield is 1 plus 0.0310 over 12 to the 12th power minus 1. So take 0.0310, divide it by 12, add it to 1. I get 1.002583. I'm going to take that to the 12th power and subtract 1 from it. 1.002583 to the 12th power. I get 1.03144, and it's a 0, minus 1, which is 3.144%. So it looks like Town Bank is the better deal. So that finishes up section 6.4.